Hey everybody, we're back. We're in section 6.3 still, and now I want to show you what's going to happen if we're trying to solve a trig equation that has a double or half angle, but substitution is not going to work. And let me show you the reason why substitution doesn't always work. Substitution means to replace one function for what it equals, one expression for what it equals. We can do substitution. The problem is we're going to create an equation that's more difficult to solve. So let me show you what I'm talking about. If you look here in our example A, we have cosine 2x is square root of 3 over 2. And we want to solve that equation for the angle x. And we notice it has a double angle. Our first mode, our first way we're going to think is say, okay, that's a double angle, I'll just do a substitution. I know there's 3 different identities that are equivalent to cosine 2x. I'll just replace them. All right, let's talk it through. I could replace this with cosine squared x minus sine squared x, but why would I not want to choose that? Right, because that would make 2 different trig functions, and we've already seen so far that when we're solving a trig equation, we want everything in terms of the same trig function. So I could replace cosine 2x with 1 minus 2 sine squared x. That could work, because then everything we would sine, but then your sine squared is negative, you'd have to make it positive. That sounds like too much work. So our third option is to replace cosine 2x with 2 cosine squared x minus 1. And I agree with you. That's a legitimate substitution. There's nothing wrong with that. We still have one trig function. Now the angle is in terms of x, which is what we did before. Here's the problem with this one. Remember, we're trying to solve for angle x, which means we have to isolate the trig function. To isolate the trig function here, we're not going to make a pretty number. We're going to make some ugly, irrational number, and let me show you. To get x by itself, cosine x by itself, we would have to add 1 over here. But to add 1 over to the right side, you need a common denominator, which would be 2 over 2. So if I add 1, I would have to add square root of 3 plus 2, which I cannot add. They're not like terms. So I'd have to write 2 plus square root of 3 over 2. That's not bad. But then I'd have to get rid of this 2 by dividing. And to divide a fraction by 2 is really multiplying by the reciprocal 1/2. All right, let's do that. Get rid of that 2. And that'll give me 2 plus square root of 3 over 4. Not bad. But we're still not done. That's not cosine x. That's cosine squared x. So you'd have to get rid of the square by square rooting. So there's the cosine x isolated. We'd have to square root this fraction. Well, you can't square root the numerator, so you leave it as 2 plus square root of 3 in a square root. The denominator is square root of 4, which is 2. And we know every time you square root, you get 2 solutions. So you're probably saying, well, what's the problem, Miss Black? Well, here's the problem. Answer the question. We got to do an inverse. What inverse, what angle will spit out this value? Are you going to see this number on the unit circle? No. Are you going to see this number on the right triangle? No. And the only thing we could use to find this angle is to type this in a calculator, but the directions say you're not allowed to use a calculator. So this is an example when substitution goes bad. If substitution makes the algebra arithmetic very complicated, then we want to avoid it. So I have another approach on how you could solve this equation. Okay. So this approach I'm about to show you is very specific. It works when you have the double or half angle identity on the left and a number, a constant on the right. There are no other terms. So both in my example A and on my example B, I have my trig function on the left and I have a constant, a number on the right. So this is when this method will work the best. What you do is you pretend that angle isn't a double angle. Let's pretend that that wasn't there. If I rewrote this and I just wrote cosine x is square root of 3 over 2. Let's pretend it wasn't a double angle. If the expression was written cosine x equals square root of 3 over 2, we'd all be jumping for joy. Because we could do the inverse of this, right? X would be the cosine inverse of square root of 3 over 2. And that puts us back to section 6.1 and 6.2. We know we can look that up because it's off one of our right triangles. It's either 30 degrees or 60 degrees. So let's see what happens if I draw my 30 degrees. Side opposite is 1, hypotenuse is 2, adjacent side square root of 3. The cosine definition is x over r, or adjacent over hypotenuse. If I put my finger on 30 and I do x over r, I surely get that value. So I know if this was just good old, that angle was good old x, that the first answer would be in quadrant 1, the angle would have to be 30 degrees. The cosine of 30 degrees is square root of 3 over 2. But because this is positive, cosine can also be in what quadrant? Let's think. All students take calculus. Oh, it could be in quadrant 4. And the angle in quadrant 4 would be 360 minus the reference angle, 30, which would give us 330 degrees. Now I know what you're saying. Ms. Black, the angle wasn't an x. The angle was a double angle 2x. So these can't be the right answers. I agree with you, but here's how we're going to fix it. These would be the answers if the angle was x. What was the angle, guys? It was 2x. So 2 times something has to equal 30 degrees. 2 times something has to equal 330 degrees. That's what you're going to do now. You're going to take these answers, which we know are incorrect because the angle would have to be singular x, and we're going to set these answers to what the angle actually was, 2x. And this is easy to solve. We'll divide by 2, we'll get 15 degrees. And we'll divide by 2 and we'll get 165 degrees. Now, I'll prove to you I'm right. Take 15 degrees and put it back up in the original. 2 times 15 is 30. You know the cosine of 30 degrees is square root of 3 over 2. Put the 165 back in the original. 2 times 165 degrees is 330. The cosine of 330 would be in quadrant 4. It also would be square root of 3 over 2. So here are 2 solutions. But you're not done. Because if you look at the directions said they wanted all the answers in this section from 0 to 2 pi. 2 pi is in radians, which means we're going to put these in radians in a minute. But 2 pi means we're going to how many degrees? 360. We're not done. These are only half the answers. Now you're going to say, what do you mean they're only half the answers? Well, think, this is only in quadrant 1 and 2. They're saying go all the way to 360. There are some more answers, and let me show you how you get them. When you do this method, because this is a double angle, you have to take these answers and think about this from the beginning of the semester. If I draw a 30-degree angle, what quadrant does my terminal ray land in? My terminal ray lands in quadrant 1. What do we say in the beginning of the semester you call angles whose terminal rays land in the same position? Coterminal. So guys, do you agree I can get a coterminal angle to this by adding 360? And that would give me 390 degrees. So if I looked up the cosine of 390 degrees, we know that's like looking up the cosine of 30 degrees, which would give us the same value. This angle's in quadrant 4. It has a coterminal angle. So I'm going to add to it 360, and I'm going to get 690 degrees. So we know if I look up the cosine of 330, I get square root of 3 over 2. Well, if I looked up the cosine of 690, I would get the same number because those terminal rays land in the same position. This ray would also be in quadrant 4. So we take our angle, which was not x, was 2x, and now we set it to these coterminal. And we solve this. So we divide by 2. And what is 390 divided by 2? Well, 2 goes into 3 once with 1 left over. 2 goes into 19, 9 times with 1 left over. That gives 195 degrees. Doesn't that fit in your restriction? If we divide 690 by 2, x equals 2 goes into 6 3 times, 2 goes into 90 45 times. Isn't this angle in our restriction? So the rule of thumb is, if it's a double angle, once you figure out in your head what your first set of answers are, make them coterminal and get the second set because you're going to get a whole nother set of answers. Now, We can't keep these answers because they all have to be written in radian. Okay? So remember, there's a bracket here on the 0, which means the answer could be 0 radians. But there's a parenthesis on the 2 pi, which means 2 pi cannot be the answer, anything smaller. Well, all 4 of these angles fit into that restriction. Let's start with 15 degrees. How do you write 15 degrees in radian measure? Well, you think in your head, 180 divided by what gives us 15? I believe it's 12. So this would be pi over 12. Does everybody agree? If you take 180 and divide it by 12, you will get 15 degrees. Everybody's good with that? Now, I don't need to do anything else but think about how many 15s are in each one of these numbers. If I take 165 and divide it by 15, I will get 11. So this is 11 pi over 12. If I take 195 degrees and I divide it by 15, I would get 13. This is 13 pi over 12. If I took 345 degrees and divided it by 15, I would get 23. So this is 23 pi over 12. And there's my 4 angles in radian measure. So, again, what do? We pretend that the double angle is not there. We pretend it's just good old x or theta, and we get what the answer should be. We take these answers and we set them equal to that double angle, we get our solutions. But then because it's doubled, there's going to be another set of answers. We get our coterminal angles and set them equal to the original 2x, and that's where we get our solutions. Let me show you one where substitution would never work. Look at B. Sine 3x equals -1. Did we learn any triple angle identities? No, we did not. Now I know what somebody's going to do. Somebody's going to do this crazy thing and tell me sine 3x is sine x times sine x times sine x. That is not sine 3x. That would be sine cubed x. So there's no way to rewrite sine 3x. Okay? We don't have a triple angle identity to substitute in. There's no way to rewrite that. So what you're going to do is pretend that angle is not a 3x. If the angle was just x, pretend it was sine x equals -1. We could look that up without a calculator, right? Where could we go? That is correct. We would go to our buddy the unit circle. 1, 0, 0, 1, -1, 0, 0, -1. Where is our sine value equal to -1? Well, sine is the y, and it's right here at 270. So if this was just good old angle x, our answer would be 270 degrees. Y'all agree? But our angle wasn't good old x. What was our angle, everybody? It was 3x. So this is what we do. We take 3x, and we set it equal to 270. 3 times something, if we take the sign of it, would spit -1. We're going to find that angle, that's something. That angle is 90 degrees. Now that should make sense. If we put 90 degrees back in the original, 3 times 90 is 270. The sine of 270 is -1. Everybody agree with me? All right, but remember, that's one solution. This was a triple angle. So what you want to think is about coterminal angles. Okay? Don't take this answer you got and make it coterminal. Go back here to the original. The original answer should have been 270 if the angle was x. Make a coterminal angle to that. Add 360 to that. If you add 360 to that, you would get 630 degrees. Do you all agree with me? But our angle wasn't x. Our angle was 3x. So take 3x and set it equal to 630 degrees. We can solve that. Divide by 3. X is 210 degrees. That fits in our restrictions. Now, guys, when we had a double angle, we did the coterminals. We had 2 sets of answers. This is a triple angle. So I don't think you're done yet. Go one more time. Again, make another coterminal angle back on the original. 630 is coterminal with, if we add another 360, 990. Do you all agree? Take 3x, set it equal to 990. Divide by 3, divide by 3. X would be 330 degrees. Also fits in our restriction. So it kind of has a pattern. If it's a double angle, you should have 2 sets of answers. If it's a triple angle, 3 sets. How are you getting those sets? You're pretending first the original angle's X, and then every time you want to get the next set, you're adding a coterminal to it. All 3 of these angles fit in our restriction, so all we need to do is write them in radian measure. We know 90 is pi over 2. 210 in radian measure. 210 is a multiple of 30. 30 we all know in radian measure is pi over 6, right? 180 divided by 6 is 30. So how many 30s make 210? 7. That's when we get 7 pi over 6. 330 is a multiple of 30. So again, 30 is pi over 6. How many 30s do you multiply to make 330? 11. And there are our solutions. Okay, so that's a different approach than, because substitution here wouldn't work at all. And over here, the substitution made it really messy. All right, we're not done. Let's look at the next one. C. Let me erase. Got 2 more to look at. All right. I'm trying to show you all the scenario situations that could happen. Sine x over 2 equals square root of 2 minus sine x over 2. All right. So the first thing I want you to notice is it's not a double angle. This is a half angle. Again, I would never want to do substitution with a half angle. Because if you go back to your 5.6 notes, sine of x over 2 equals plus or minus the square root of 1 minus cosine x over 2. Do you really want to replace this with a square root symbol? Heck no. That would make the algebra so much more complicated. So if it's a half angle, I do not want to do substitution at all. So the problem is here, you have a trig function on the left and a trig function on the right, and we just talked about this. To do this other method, you want your trig function on the left and your number on the right. Well, we can fix that. We can move this term to the left side by adding. And that will work because these are alike. A sine x over 2 is just like a sine x over 2. The boo-boo's going to become, you guys are going to want to add the angles. Think about algebra. What's x plus x? 2x. What's y plus y? 2y. You don't change the letter when you add. You add how many of those terms do you have? So if I have sine x over 2 and you have a sine x over 2, this means I have 2 of these sine x over 2's. 1 plus 1 makes 2. All right? Well, we're almost there. Is the trig function isolated? No, because this 2 can move because it's connected by multiplication, so I can divide. So this is going to cancel, move that coefficient, and we get sine x over 2 is square root of 2 over 2. And that's what we want. We want the expression, the trig expression, either with the half angle or double angle isolated. So it's isolated. Y'all agree? Great. Now, again, we still don't want to do a substitution. We do not want to replace this with that big identity with the square root. It's too much work. So an easier way is now we pretend. Pretend this didn't say x over 2. Let's just write it as sine x is square root of 2 over 2. Well, we know we can look that up. And we all know the square root of 2 over 2 comes off of which triangle? The 45. So we know angle x would have to be 45 degrees. And that's in quadrant 1. We also know sine is positive in quadrant 2. So the angle in quadrant 2 would be 180 minus 45, which is 135 degrees. Everybody agree with that? Beautiful. But here's our problem. Our angle wasn't just an x. Our angle was a half angle. So we're going to set these angles equal to the angle x over 2. So that's what we're going to do. We're going to go over here and say, okay, our angle is really x over 2. So x over 2 has to equal 45 degrees. X over 2 has to equal 135 degrees. We'll multiply. X is 90. We'll multiply. X is 270. Let's see if that makes sense. If I take 90 degrees and put it here, 90 divided by 2 is 45. The sine of 45 would be square root of 2 over 2. We put 270 here. 270 divided by 2 would be 135. The sine of 135, quadrant 2, would also be square root of 2 over 2. So these are two viable answers. But are we done? Well, this is a half angle. Okay? So again, it's talking about coterminal angles. Well, I know what you're thinking. You're saying to make these coterminal, instead of adding this time 360, we'll subtract. Well, that won't work. Because if we subtract 360 from either one of these, we'll get what kind of angles? Negative. And in our restrictions, we don't want negative. So the only thing we can think about doing is saying, well, what happens if we add 360? Would that make sense? Well, if I add 360 to 45, I would get 405 degrees, right? And if I add 360 to 135, I would get 495 degrees. What happens is if I go back here and set those coterminal angles equal to my angle, which was x over 2, what's going to happen is when you solve for x, well, when you solve for x here, you're going to get x is 810 degrees. Well, that's too big because it doesn't fit your restriction. So we don't need to go any further and find any more answers. Make sense? So if we look here, all we have to do is give these in radians, which we know is 90 degrees is pi over 2. 270 degrees is 3 pi over 2. So we didn't need another set of answers for the half angle, because if we made coterminal angles, it was too much. It went over your restriction. All right, let's look at one more. The last one. All right, let me get my notes. All right, the last equation we want you to solve is sine pi over 2 equals cosine, not pi, theta over 2. I apologize. Sine theta over 2 equals cosine theta over 2. All right, first thing we notice is we're dealing not with an angle, that's 1. We're dealing with a half angle. Everybody agree? Okay. Not only are we dealing with a half angle, we're dealing with two different trig functions, which is bad. And they're both in lowest terms. Can't do anything lower with sine, can't do anything lower with cosine. So your first thought is, I'm just going to go get those half angle identities. I'm going to tell you that's a bad move. Do you really want to substitute in here the square root of 1 minus cosine theta over 2 and have to deal with a square root? Normally, most people don't want to do that. Not only does it have a square root, it has a fraction in that identity. So that's two whammies we don't want to deal with. So there is another way to work this equation. My first problem is not the half angle part. Okay? Right now, we don't have it equaling a number. So I can't find out what the angle theta would be because I don't have it equaling a number yet. Right now, I have two different trig functions. So my goal is I got to get one of these trig functions out of here. I don't want to use the half angle identities. They're too messy. So what can I do to this equation to keep it balanced, but yet change the way it looks so I could use an identity? Remember back to section 5.1, those fundamental identities that we had to memorize? Well, one of the identities was sine is 1 over cosecant. Well, that's not going to help. One was cosine is 1 over secant. That's not going to help. But then there was an identity that said sine squared x plus cosine squared x equals 1. So do you agree if I could get these to be squares, I could use that Pythagorean identity? Now you're going to say, how do I get a square in there? Well, from algebra. You've learned equations of balance. If you square the left side and square the right side, it keeps balance. I'm going to show you and prove to you why that works in algebra. Here's an equation in algebra. The square root of x equals 5. You learned to get rid of the square root, you do the opposite operation. You square the left. To keep balance, you square the right. You learned in algebra, squares and square roots are inverse operations. They cancel out. That gives you x. On the right is 5 squared, which is 25. You know if you check that and put it back, the square root of 25 is 5. So if you've learned way back when in algebra, if you square both sides of an equation, it keeps balance. Okay? Well, that's what I'm going to do. I'm going to square the left side. I'm going to square the right side. I'm going to rewrite this as sine squared theta over 2 equals cosine squared theta over 2. What that allows me to do now that I have a square, I can use that Pythagorean identity. We learned sine squared theta plus cosine squared theta equals 1. If I want to replace cosine squared theta, I'd move that sine squared theta. And I know cosine squared theta is 1 minus sine squared theta. Correct? Well, that's what I'm going to do here, guys. I'm going to replace this. Now that I made it a square by doing legit, balancing both sides, I can replace this with 1 minus sine squared theta over 2. And now if you look, we have the same trig function. Yay, hey, that's what we wanted, the same trig function. And now I can move this sine squared over here by adding. So I'm going to add my sine squared theta. And again, let's not make mistakes. X squared plus x squared is not x to the 4th. So don't tell me sine squared theta over 2 plus sine squared theta over 2 is sine to the 4th. These are like terms. They're identical. So 1 and 1 makes, I have 2 of these. I have 2 sine squared theta over 2 equals 1. Is my trig function isolated? No, I can move that 2 by dividing. I get sine squared theta over 2 equals 1/2. I have to get rid of the square because I just want the sine, the original trig function. Sine theta over 2 equals, when you do a square root, you have both a plus or minus. We're square rooting 1, which is 1. We're square rooting 2, which is square root of 2. But we have not written 1 over square root of 2 since the beginning of this semester. This is really square root of 2 over 2. And it's both positive and negative. So now we're back to where we started. If I know sine theta over 2 equals plus or minus square root of 2 over 2, I know I have a half angle there, so I'm about to pretend. I'm about to make believe that that angle's not there. I'm going to pretend that angle is just good old theta. If theta If I want to just know theta, I would do the inverse of sine for square root of 2 over 2. We all know by now, by the end of the semester, square root of 2 over 2 is what angle? 45. Now, here's the catch. Theta is not just 45, because sine can be positive in both quadrants 1 and quadrants 2. So in quadrant 2, this would be 180 minus 45, 135. But because we did a square root, and square roots are both positive and negative, this fraction value is also negative, which means the angle could be in quadrant 3 for sine to be negative, or quadrant 4. So if the reference angle is 45 degrees, what would the angle in quadrant 3 be? Well, it would be 45 plus a 180, which would make 225. And if it was in quadrant 4, it would be 360 minus the 45, which is 315. So because to isolate the trig function, you had a square root. Square roots always have positive and negative answers. Sine is always positive in 2 quadrants. Sine is always negative in 2 quadrants. Now we deal with the problem. The angle wasn't just good old theta. What was our angle, everybody? That's right, it was theta over 2. So I take all of these and I say, okay, theta over 2 is 45 degrees. Theta over 2 is 135 degrees. Theta over 2 is 225 degrees. Theta over 2 is 315 degrees. So theta could be 90. Theta would be 270. Theta would be 450. Theta would be 630. So these are not the answers, because this is us pretending the angle was just good old theta. But because the angle is really a half angle, these could be the possibilities. Well, go back to your restrictions. Can only be as big as 360. Goodbye, goodbye. Everybody's good with that so far? Awesome. Now here's the problem. These are both not the right answer. And again, you're going to say, well, why, Miss Black? Why are they both not the right answer? They fit the restrictions. Because it goes back to understanding algebra. I said to solve this equation, we eventually had to do a square root, right? And to even get started with the square root, we eventually had a square. Let me show you an example in algebra where you square root both sides and the answers don't check. If you remember in algebra, if I asked you to solve this equation, square root of x equals -5. You're right. To get rid of the square root, you would square both sides, which keep in balance. That's what we did here. You agree. This would cancel out. You get x equals. I agree. -5 squared would give us 25. But we talked about in college algebra, when you change the way the equation's set up, when you make a dramatic change in an equation and you take out some kind of symbol, even though you kept balance, you're not guaranteed your solutions always work. Because guys, if you remember, if I go back to check this in the original, here's the original. If you go substitute 25 in here, the square root of 25 will never equal -5. Because when we have that symbol already there, it's understood give the positive. So back in algebra, you had to say, this is not the right answer. There is no solution. So we know even though squaring both sides does keep balance, it's a legitimate move to rewrite both sides of an equation. When you square both sides, you're not guaranteed your solutions will check. So guys, for us to really know if 90 and 270 are correct, we always go check in the original. So everybody go here, put 90. 90 divided by 2 is what? 45. The sign of 45 we all know is positive square root of 2 over 2. If I put 90 here, 90 divided by 2 is also 45. The cosine of 45 is square root of 2 over 2. 45 degrees for both of these are in quadrant 1, which means both answers would be positive. This checks. If we put 270 back in the original, 270 divided by 2 is 135. The sign of 135, that is not in quadrant 1, that's in quadrant 2, and the sign in quadrant 2 would give a positive number. If I put the 270 here on this side, the right side, 270 divided by 2 is still 135, but now we're doing the cosine of 135. Cosine of 135 in quadrant 2 is not positive, it is what? Negative. And there's no way the sine of 135, which is positive, is ever going to equal the cosine of 135, which is negative. Therefore, this answer does not check. And 90 degrees, which written in radians is pi over 2, is the only solution here. So, this section 6.3 is a little bit trickier. Okay, you're going to take your time. If a substitution with a double angle or half angle will work for you, great, do the substitution. But if it doesn't substitute, we have to look for other means to solve this equation. Okay, we have one section left on solving equations. I'll see you in the next video.